Induced EMF or electromotive force. In the electric circuit chapter, we talked about electromotive force. It is actually a potential difference between 2 points that is measured in volts. It is not a force, but it's a historical term that has just not gone away. Because of its unfortunate name, it is frequently just referred to as EMF or this script-looking E here. It represented the maximum possible voltage from a battery during the electric current section before it was reduced by the battery's internal resistance, and then if you'll recall, that was called terminal voltage. This chapter is going to show a way that a voltage can be developed in a conducting wire that is not connected to a battery. Ørsted and Ampere both showed that a current will generate a magnetic field. If you're a physicist, what's the next thing you want to check up? Of course, you want to see if the reverse can be true. Can a magnetic field generate a current? Michael Faraday, we've talked about him before, was able to make this connection in 1831. However, the magnetic field had to change, either in magnitude or orientation to the wire where the current was being created. Don't worry about that yet. We'll show pictures and go into more detail. The interesting part, in America at the same time, Joseph Henry discovered this phenomenon, but he didn't publish it. Faraday published it first, so he gets credit for it. But don't feel bad for Henry. They named the unit of inductance Henry in his honor. This happens a lot in mathematics and physics. For example, in calculus, Newton in the UK developed it, and Leibniz in Germany developed a very related form, both at the same time, independent of each other. And depending on what country you're in, that's who they claim created calculus. UK, you would say it would be Newton, and in Germany, Leibniz. Here's a schematic of the experimental setup that Michael Faraday used. He connected a battery, here's your battery, to a metal coil via insulated wires. And the whole point of this coil is just to magnify the magnetic field. It increases the magnetic field due to the magnetic field generated by these wires, by the current in these wires. Now let's look at this. Never is there any current in this metal coil. That's what this comment is. Never any current there, just the magnetic field. These wires are insulated. No current passes through them to the coil. So when I close this circuit, current will go like this through the wires, never going into the coil, and then back to the other end of the battery. If the current is steady, so if you've had this battery hooked up for a real long time, there's absolutely no voltage or current developed over here. And what do we have on this side? We have a wire wrapped around, comes back, and this is a voltmeter. So the voltmeter reads 0 when the switch is open, and it would also read 0 after the switch was closed for a long time. However, what Faraday and Henry also found, when you close the switch, you will get a current, and then later when you open it, you'll get a current. That's kind of wild. When the switch was closed, see here the switch is closed here to that red line, the ammeter, this guy here, in the secondary loop, that's what we're going to call this loop here that doesn't have the battery, gave a positive reading, indicating a counterclockwise current flow. However, after the switch had been closed a short time, the ammeter went back to 0. There was no current flowing in the secondary loop, but you still had current flowing in the primary loop. It's only when the current changed did you get an ammeter reading. When the switch was then opened again after it had been closed, see it's open like this, the ammeter in the secondary loop gave a negative reading, indicating a clockwise current flow in the secondary loop. After the switch had been open a short time, the ammeter went back to 0. There was no current flowing at all here. What was cool here is you had current flowing in the secondary loop, although there was no current in the loop with the battery. Something was induced over here. We'll show 2 more examples of where a voltage and a current were induced without a battery. This is Faraday's disc generator. It looks like something you'd slice bologna with in a deli. You have a metal disc here, and you have a little handle here that you can spin it. Here you have a magnet, a horseshoe magnet, and what happens is as you spin this metal wheel, the points on the wheel will see a changing magnetic field. Here you'll have a strong magnetic field, then as you go far away from it, the magnetic field gets weaker and weaker. Therefore, since this magnetic field is changing, a current will be induced that is picked off the disc here by this little brush here. Here's one connection, and here's the other connection. And you can have a current that you can take off to an ammeter and measure. A bar magnet over here that moves towards, through, or away from a loop of wire will generate an EMF and then a current in the loop. A current will flow in here just because you're moving the battery. A current will also be generated if the magnet stays constant, doesn't move, and then you spin this loop around an axis like this. So you're kind of spinning it out of the page. You will find an induced EMF and a current. If you just hold the magnet there and the loop isn't moving, no current is generated in the loop. It's now time to explain what's going on. We now have evidence that a magnetic field can generate a current. But there is a difference between this and a current generating a magnetic field. A steady current will generate a magnetic field. We did that in the last unit. However, a steady magnetic field and a non-moving constant area loop of wire will not result in a current in the wire. However, a constant magnetic field and a moving loop of wire will result in a current. A changing magnetic field and a stationary loop of wire will result in a current. A constant magnetic field and a changing area of the loop of wire that the field goes through will result in a current. That's a lot for one paragraph, and we're going to go through that in some detail and make it a lot clearer. But first, we're going to have to define magnetic flux before we can fully understand what's going on.